This is CERN at Geneva, where they're building one of the biggest machines in the entire world, in search of some of the smallest particles in the universe, particles that haven't been around since the time of the Big Bang.
This program is about the universe, how it was made, how everything in it was made, and the huge new experiments that are being done to investigate it. I'm visiting the most daring of all, the world's biggest experiment, buried under Geneva in Switzerland, where they're recreating the Big Bang. We'll also take you on a sickening flight, where they're trying to find out how the planets were made. We'll join the team attempting to probe the stuff we're all made of, stardust. Only they're not sure whether they've found it yet. And we'll meet the man who thinks he knows how to make universes, though he doesn't always get it right.
I have a filing cabinet full of failed universes. They're to a penny.
My journey back to the beginning of the universe begins by heading 100 meters underground. This is the Large Hadron Collider, and it's huge. 27 kilometers of tunnels and caverns under the city of Geneva. It's one of the world's most powerful machines, and it needs to be this enormous because the scientists here are going to blast their way back 14 billion years by creating a mini Big Bang. This machine's job is to smash together protons, the guts of hydrogen atoms, with such energy that the resulting fireball will have a temperature of 10,000 million degrees Celsius. The breakthrough that made it possible is this, the world's best magnet. To make a mini Big Bang needs protons going so fast that over 1,000 of these huge magnets are needed to steer them round a circle. The speeds involved are truly amazing, as engineer Verena explained to me.
Our protons here are very close to the speed of light. I think if I get it right, it's 99.99999% of speed of light at top energy. Yeah.
Wow. The power needed to do all this is so vast that France will only let them run flat out in the summer, when they don't need the electricity to warm people's houses. This experiment depends on the idea that to find out how the universe is made, you first have to go right back to the start, when all the ingredients were in place but hadn't yet formed stars and galaxies. The collisions they make here will have enough energy to create particles that were around only fractions of a second after the Big Bang.
But how can we be sure there was a Big Bang? Well, perhaps the greatest single revelation about how the universe was made came from a series of rather simple telescope observations made in the 1920s, made in California by a chap called Edwin Hubble. And the implications of his observations were quite extraordinary. Janet Sumner went to visit the place where he turned science on its head.
This is the Hooker Telescope on Mount Wilson, just a couple of hours from Los Angeles. In the 1920s, this was the best telescope in the world, and it's the instrument that Edwin Hubble chose for his survey of galaxies.
Hubble's twin weapons were the sheer volume of data he collected and an ability to cut through it to see what it meant. In the 1920s, Hubble helped solve a huge debate about the size of the universe. Using this telescope, Hubble proved that the universe was much bigger than anyone had thought and filled with galaxies, some of them at unimaginable distances from the Earth. Don Nicholson's dad worked with Hubble, and Don himself has been coming here since he was a boy.
This place is a shrine. During the first half, really, of the last century, there was no observatory in the world that was the mecca for astronomers that the Mount Wilson Observatory was.
Your dad was a colleague of Hubble. Did he tell you much about him as a man?
Not a great deal. He didn't socialize with the rest of the staff at all. As an observer, as an astronomer, he was tops. He was A1. But as a man, as an individual, well, not everybody liked him.
Having measured how far away galaxies were, Hubble now wanted more detail, so he set about recording spectra from galaxies. He wanted to find out how they differed from sunlight here on Earth, and in particular, were they shifted towards the blue or the red? Hubble knew that objects moving through the universe would slightly change their colour. A star or galaxy moving towards you would look slightly bluer, going away would look slightly redder. Hubble set out to measure the blue shift and red shift of thousands of galaxies. Although some nearby galaxies were blue shifted, with the distant ones it was a completely different story.
All of the galaxies that he looked at were redshifted, and that could only mean one thing: everything in the universe is moving away from us. Imagine that these drawing pins are galaxies moving away from the Earth. Hubble discovered that they don't move like this, all at the same speed. Now, my galaxies are at 10, 20 and 30 centimetres, and if I stretch the elastic to double its length, the first one has only moved 10 centimetres. The second one, which was twice as far away from Earth, has moved twice as far, and the third one 3 times as far, and so on. This is exactly what the galaxies did, and Hubble came to the inevitable conclusion that just like the elastic, the whole universe is expanding.
The result was shocking, because by tracking the expansion back in time, it was possible to work out when it started. It turned out that the universe began nearly 14 billion years ago in what became known as the Big Bang.
Looking far out into the cosmos would seem to be a reasonable way to find out how it was made. It's less obvious how burying a huge machine deep underground is going to tell us anything about events that happened 14 billion years ago.
CERN, the European Nuclear Research Centre, was built just after World War II. Its job was to find out what atoms are made of by smashing open the tiny particles inside them. It was at the cutting edge of physics for 40 years, culminating in the digging of the 27-kilometre tunnel, which was opened in 1989. Now they've ripped out the old machinery and replaced it with a new collider that's 10 times more powerful, that will peer not only inside atoms, but at the beginnings of the cosmos. An idea I find quite mind-boggling. So I asked Ben Allanach, who dreamed up some of the experiments here, to explain what they're hoping to find.
We hope to be learning more about the very start of the universe.
Sorry, the start? You mean the Big Bang?
Just after the Big Bang, yes.
How long after?
The first second.
The first second? But I mean, you don't need to dig a 27-kilometre tunnel underground, do you, to do that?
Yes, that's exactly what we need to do.
I see. OK. Now, what are you hoping that they'll find?
The Higgs boson, I hope they'll find.
Why are you interested in this elusive thing?
That's the particle responsible for mass.
But I thought Newton sorted mass out a long time ago.
Newton sorted out how gravity and forces interact with mass, but not where the mass comes from in the first place.
OK, so the Higgs boson is what gives things mass?
Yes, that's right.
I can see it might be quite interesting to find that. Anything else you might find apart from the Higgs?
You might be able to produce dark matter if we're lucky.
Dark matter?
Yes, if the theories are right.
Dark matter was first detected in galaxies, when it turned out that normal matter, the stuff we can see, doesn't make enough gravity to keep a galaxy together. It seems there's an awful lot of dark matter about.
This is the universe, and the stuff you can see, this is in the right proportion. The stuff you can see are the coloured jelly beans. All the rest is stuff that we can't see.
But that's more than 90%.
That's actually 96% of the universe. We don't know what it is, and we can't see it.
Losing 96% of the universe seems a little careless. Although we don't know what dark matter is, it's a vital ingredient in assembling a universe, at least according to Professor Carlos Frenk from Durham, and he should know because he's made hundreds of them.
What we are trying to do is replicate what nature did on a small scale. We construct model universes, toy universes, and that gives you a sense of power that you can make a universe, but of course it's just a universe in a computer.
But to find out how the universe has developed over 14 billion years, Carlos needs one of the most powerful computers in the UK.
This supercomputer is capable of carrying out 300 million arithmetic operations per second. You require lots of computing power because the universe is very big and it's very complex and it has lots of things in it, which is what we're trying to reproduce.
The supercomputer uses 3 equations, all laws of physics which apply to you and me here on Earth. Each run of the simulation takes a cube of universe containing about 10 billion particles, and they run it for 10 billion years, which on the computer takes only 2 months. The universe Carlos ends up with can look surprisingly like the real thing, but not always. The recipe for cooking up a universe is the known laws of physics, however the ingredients are less certain, and it can all go horribly wrong.
These are 2 attempts to simulate the universe. They differ in a relatively minor detail. This one has cold dark matter, and this one has warm dark matter. Yet, the evolution of the 2 is radically different.
In these universes, Carlos is trying out 2 possibilities. On the left, the dark matter is made of cold, heavy, slow particles. On the right, they're lighter and faster and warmer. It soon becomes clear that one of the universes isn't working. While they both develop the same big structures, the universe with warm dark matter never forms the small clumps and lumps that will go on to be galaxies. Carlos and his team know when they've got it right, because now, for the first time, there's a digital survey of a huge chunk of our universe that makes it possible to compare the model with the real thing.
After months, sometimes years of effort, when you suddenly see the first image that comes out, and you say, yes, this is it, this looks like the real thing. Those moments are immensely special, and I've had only a few of those in my life.
Having made a universe, the Durham team has now used its DIY skills on something smaller, a single galaxy. Does the recipe still work at this much more detailed level?
The computer-generated galaxy and the real galaxies are virtually indistinguishable, telling us that our story, our cosmic story, must have some resemblance to what happened in the real universe.
When Carlos Frenk was putting his universe together, he knew he needed dark matter, though he didn't know what it was. The best hope of actually getting our hands on a dark matter particle is here at CERN.
You might have thought that making a mini Big Bang would be the difficult bit, but actually working out what happens afterwards is just as hard. And that's the job of the ATLAS detector.
ATLAS is one of the biggest and most complicated machines ever built. The size of it is overwhelming. 48 meters long, 25 meters in diameter, in a cavern the size of a cathedral, and the whole thing built 100 meters underground. ATLAS sits in the 27-kilometer ring at CERN, and it's here that protons at nearly the speed of light smash into one another. ATLAS's job is to detect fragments exploding out of the resulting mini Big Bang. One of the scientists building this vast machine is Pippa Wells.
If you can see, there's a hole there.
In the middle?
In the middle of that disk. That is where the beam pipe from the accelerator will finally go.
So the protons are going to be whistling in through and out of that hole in the middle?
That's right. So bunches coming in from this side, same thing coming in from the other side. 40 million packets of protons every second have a chance to collide in the middle of the detector. And something like 20 of those protons will interact. So we're looking at the remnants of what was briefly created in the middle, and then those remnants fly out in all directions.
So you're saying 2 protons hit, there's a fireball, a massive or minute explosion,
tiny fireball,
but
yes.
incredibly hot.
Yes.
And whatever is formed will then instantly break down into other bits.
That's right.
ATLAS is so huge because it's made of layer upon layer of detector, designed to work out what went where and when. Pippa is responsible for the detectors at the very centre of ATLAS, closest to the collision. But detecting the particles is just the beginning. The next challenge is getting the information out down 50,000 separate cables.
What we then have to do is work out, was this an interesting event? Are these the remnants of some new particle we've never seen before? Is this a clue for the Higgs boson or for dark matter? Or is this just some ordinary interaction? It's the sort of thing we've seen at previous accelerators, it's just happening now at higher energy.
Right.
It won't be humans deciding which collisions are interesting. ATLAS can handle 600 million collisions a second. Ultra-fast computers analyse events as they happen and decide which are worth recording and which can be thrown away.
This is a very big bit of apparatus you've got here, isn't it?
It certainly is, yes.
Are you sure it's going to work?
Yes.
Inside Atlas, they're recreating events at the very start of the universe. But CERN isn't the only place to try making bits of the universe for real. About 1 billion years after the Big Bang, the stars were starting to shine. Now it is possible to make stars on Earth. Janet went to see how you do it, and why artificial stars might one day save the planet.
In this ordinary-looking warehouse in the heart of Oxfordshire, Andy Kirk makes a star every 15 minutes.
Making stars takes a lot of power. Real stars are made by gravity squeezing clouds of hydrogen. In Oxfordshire, they use electricity to make an incredibly strong magnetic field to do the same thing.
Normal stars like our Sun form when huge clouds of hydrogen collapse in on themselves. The immense heat and pressure in the core of the new star causes hydrogen atoms to smash together and make helium, releasing enough heat to make the star shine. It's called nuclear fusion, and it's what they're doing here at MAST.
MAST stands for Million Amp Spherical Tokamak. 1 million amps of electricity, and tokamak is the Russian name for the chamber where fusion takes place.
Andy, this is an amazing piece of kit. What actually happens here?
This is our star maker, and to date we've made 16,000 stars with it.
Why is it so important for you to recreate what goes on in the stars?
Nuclear fusion is the process which powers the Sun and all other stars. Our aim is to recreate those processes here on Earth, harness the energy that's produced, and therefore be able to satisfy mankind's need for electricity and other power generation for more than 1 million years. Let's go this way.
So Andy's dream is to harness star power to produce energy without fossil fuels, without greenhouse gases, and with no significant nuclear waste. If it sounds too good to be true, it is. For the moment, this machine is strictly for research.
Preparing shot 16923.
Stars are made from plasma, a state of matter beyond solid, liquid and gas, and found in fluorescent lights as well as stars. The 4-metre star-making chamber is filled with hydrogen plasma, which is heated until the atoms fuse. The challenge is to contain it. The plasma has to be kept away from the walls or it collapses. The MAST team is finding out how to keep their stars stable, so they replay each one in ultra-slow motion. At real speed, each star is born, burns and dies in half a second.
That is the closest you come to creating a star on Earth. The centre of that plasma is at a temperature of 20 million degrees centigrade.
Why does it have to be so incredibly hot?
You need the heat in order to cause the particles to fuse together. They only fuse if you can get them very, very close to each other. To do that, they have to be travelling incredibly quickly, which means that they need a very high temperature.
Does it behave in any way like our Sun?
It has many of the features of the Sun.
Wow, what did it do then?
That is one of our solar eruptions. It's an instability in the plasma when the plasma is saying, oh, I don't want to be in this state, and it erupts, throwing out particles, very similar to what you see in solar flares. They're a little like young children in that they're very much full of energy, and they don't really want to be told what to do. And when we tell them to do something they don't want to do, they tend to throw a tantrum.
Throws all its toys out of the pram.
That's a good analogy, yes.
When real stars explode, it's not so much an end as a beginning, because the stardust that is shot out into space is one of the most important raw materials in the universe. Stardust might go on to form another star, or a planet, or even a person.
We have main engine start, 0 and...
Now, NASA has brought some stardust back to Earth. First, they had to find it. The Stardust spacecraft went out past Mars to a place where dust from beyond the solar system was thought to be streaming through. The next problem was how to capture it, and for that they turned to some very odd stuff indeed, as NASA's Andrew Westphal explains.
Aerogel is about the weirdest thing that I've ever worked with. It's only a few times as dense as air. It's almost like a ghost. Almost doesn't exist. I'm holding a piece now in my hand. and I can just barely feel its weight. It is foamy glass, really, and has the almost magical property that it can capture particles moving many times the speed of a bullet.
The aerogel was mounted in a sort of tennis racket, held out into the stream of dust. But this dust is very rare. NASA worked out they might have captured as few as 45 dust particles in all. Before returning home, Stardust had an important rendezvous with comet Wild 2. Comets are what was left over when the planets were formed, and the dust in a comet tail should have clues about what conditions were like when the Earth formed. So it was out with the tennis racket again, this time using the other side. Then it was packed safely away to survive landing on Earth. The capsule containing the precious dust touched down safely in the Utah desert in January 2006.
It is absolutely extraordinary that these samples came back to us. This is the first time that this has happened since the Apollo days, when we got the first moon rocks back. And in fact, these are the first solid samples that we've ever gotten back from beyond the moon. So we're incredibly excited.
With the aerogel safely back in the lab, the team realized they had a problem. They couldn't find the Stardust particles.
They're about 1/millionth of a meter, 1 micron in size. That's about 100th the diameter of a human hair.
Photographing all the aerogel at high enough magnification to see them has produced an overwhelming 60 million images, all but 45 of which contain nothing at all. Andrew and his team have come up with a novel solution. They're using thousands of volunteers online to help with the search for Stardust.
The average person has scanned over 1,000 fields of view, which is a tremendous amount of work. They are looking for the tracks that the particles make when they hit the aerogel and stop. And here's one in this corner, and the track is here. This is very subtle, but people are finding things like this. It's absolutely fantastic.
Meanwhile, another team has been looking at the comet dust particles, which are much easier to find. The high-speed collision makes a cone-shaped track in the aerogel, with the comet dust particle trapped in the sharp bit of the cone. Already, there are surprising results.
It could have been that we got these samples back and every particle track was about the same as any other. Instead, we're finding that they're as different as night and day. And even within one particle track, we see one side of the track might be full of nickel, another side of the track might be full of iron. And we really don't understand that yet.
As for the Stardust, the search goes on. Once they do find it, NASA are confident that, just like the moon rocks in the 1970s, this stuff will be revealing its secrets for generations to come.
At least in outer space, there are some solid particles to collect. Here at CERN, it's not so easy.
The trouble is, they're trying to capture an event that really can't be captured. When the particles explode, it would be great to record it at the exact moment it happens. But Atlas can't see anything until the first particles reach the detectors. But by the time this happens, some of the particles produced in the original explosion will have broken down, so they'll only see fragments. To find out what happened in the fireball, Atlas will have to wind back time. They've kindly let me bring my snooker table into the Atlas cavern to show you what I mean. I'm going to produce a tiny explosion at rather less than the speed of light. The white paint does the job of the Atlas detector. Just as in the real Atlas, all that's left after the explosion are the tracks of the particles. It's like arriving at the scene of a car crash and trying to find out what happened. Can I work out what went on?
The cue ball hit one almost straight on, so this one went on there. You can see the track, bounced off here. This is the reverse track through here, where it collided with another one and knocked it up there, hit the paint box and wound up there. Meanwhile, the third ball went from here down that way and up there. The cue ball eventually rolled through down there. Quite complicated, isn't it?
And if I really wind back time, you'll see that I got it slightly wrong. The Atlas scientists will do this time-travelling detective work to see whether among the millions of collisions there is one that shows they have briefly created the Higgs particle that is responsible for mass, or even a particle of dark matter, the unseen stuff that holds galaxies together. In this programme, we've seen attempts to recreate on Earth the Big Bang, the formation of a star, galaxies, and even whole universes. But there is another mystery rather closer to home. How was the Earth made and the other planets? The theory is that from the cloud of dust and gas that made a star, a disk forms. In it, dust clumps together, forming bigger and bigger lumps, and eventually gravity will pull them together into planets. But this will only work if the lumps actually stick together, something that has puzzled astrochemist Helen Frazier.
We know how the big things stick together with gravitational forces and how the small things stick together with the attractive forces between them. But the problem is that when we get to this gap between millimetre sizes and kilometre sizes, we actually don't know how the particles stick together at all.
Helen tried to recreate the beginnings of a planet by firing centimetre-sized lumps at each other to see if they would stick. But the results were disappointing.
What happens is gravity acts on the particles, and before they get anywhere near hitting each other, they just disappear out of the field of view of the camera and hit the bottom of our vacuum chamber.
So Helen took her team and equipment for a flight 20,000 feet above the Mediterranean in an attempt to get closer to conditions in space. About a third of passengers in the so-called Vomit Comet get ill, but this stomach-churning parabolic flight is the closest Earthlings come to escaping the effects of gravity.
You'll hear the pilot say the word injection. He's French, so he says it in a very nice accent. And what happens is you start floating off the ground. And as you start floating off the ground, this is really where you have microgravity. And that only lasts 22 seconds. And what's very important at the end of 22 seconds is the plane has to pull back out of the parabola. And it has to do that at the same angle it went in at, i.e. that 50 degrees upwards becomes 50 degrees straight downwards towards the sea. It might seem quite scary for the pilots who are just looking at the sea, but again, for us inside the aeroplane, what we feel is another 2G force. And we repeat this 31 times during a flight. And generally that takes about 4 to 5 hours on an aeroplane with no toilet. We work in a team of 3, and each person has a very specific job. So as soon as we hear the injection sound, they have to turn a little particle holder so the particles are aligned and ready for the pistons to fire and push the particles towards each other until they collide. Then another member of the team will actually fire the pistons, and you hear the pistons move, and there's something like The role of the final person is simply to start and stop an ultra-fast camera which is recording exactly where our particles are moving and what's happening. We try and do this 2 to 3 times per parabola.
Even under these conditions, the particles don't stick. The next round of experiments will be even more extreme.
Basically, we're going to try and get to very low temperatures, minus 200 degrees C, and coat the particles in ice so we can see the effects of ice and low temperature on this sticking process and maybe work out how the baby planets are actually formed.
This is a really exciting time to be working on how the universe is made. In the last 70 years, we've gone from discovering the Big Bang to recreating some of those conditions right here at CERN. What's more, we've discovered that not only are humans not the centre of the universe, but the world we live in, what we see, what we touch, what we feel, is only a microscopic part of the whole cosmos. For 2 free posters telling you more about the series, or for information about other Open University programmes on the BBC, call 0870 900 0312 or visit open2.net.
To the Highlands next on BBC Two for a great British journey.